right, let's talk about what can go wrong with your prediction model. So, what can go wrong? The first thing that can go wrong is you just fit a bad model. The next is something known as quantitative extrapolation. And we're going to talk a little bit about what this means, but basically this is like when you're trying to predict for X values that are outside of the range that you observed in your initial data. Another thing that can go wrong is qualitative extrapolation. And so this is has less to do with the range of your X's and more to do with the actual population that you were sampling from versus the population that you're building predictions on. Another way things can go wrong is overconfidence due to overfitting. And so this is your model could look really, really good depending on what metrics you're using to measure success, but maybe those really aren't the right metrics to use. And then finally, you can just have black swan events where basically your data looks good, your model looks good, kind of everything checks out. You're not extrapolating outside, you're using it kind of in the same range, but there are just these really uncertain events that can happen that can really dramatically change your estimates. So a bad model, what do I mean by that? Well, this is an example of a bad model where your model just really isn't appropriate for your data. And so my model here is this blue line. It's a linear regression model trying to predict y from x. And if you notice from this plot, the relationship between x and y is truly quadratic. And so by that, I mean that really we probably should be including a squared term. You can see here there's this U-shaped relationship between x and y. But I'm trying to just fit this straight line, and I'm doing a pretty bad job. Basically, with the exception of kind of 2 points where my prediction model intersects with this model, I'm really doing a very inaccurate job of a prediction. So bad models are just characterized by, they don't fit the data well. It's a bad statistical model for your data, and that's easy to assess by basically doing some models checking or model evaluation afterwards, which we'll talk about next time. The next way something can go wrong is by something known as quantitative extrapolation. And so here's an example where I actually have a good model. Now the relationship between x and y is truly quadratic, and that's the linear model that I fit. I fit a model that includes both x and x squared. And so I am fitting the right model to this data. And by all accounts, when I look at this model, when I do my model checking, when I'm evaluating my model by the metrics that we're going to talk about next time, I see that this model looks pretty good. It looks like it fits the data well. So where can things go wrong? Well, if this is my output from my model, and let's say somebody asked me to get a predicted value when x equals 10. So how would you do that? Well, from just this information, we know how to get that value. We just talked about calculating predicted values. In fact, we know how to even get a prediction interval on that value. We would just take the beta hat values from this model, so that'll be from this column right here, and we're going to take an x naught value here, which is going to include, it'll basically be 1 for my intercept, and then it'll be my x value, which is 10, and then it'll be x squared, so that'll be just 10 times 10, so 100. And then we're going to transpose that and multiply it by my beta hat, so the 0.056, 1.01, and 0.95. So we know how to do that. So I could do that in R. For example, here I've created a vector here for my x0 with 1, 10, and 10 squared. So again, the 1 is just because I know I want to include my intercept, and then 10 and 10 squared are for x and x squared. And then I've got this beta hat, which I've just pulled directly from this model. And I can take the transpose and multiply it by beta hat, and I end up getting 105. Okay, great. So when I have an x value of 10, I have a y value of 105. That's what my prediction is. And I could use those variance calculations that you did last time to be able to get a standard error as well as a confidence interval for this. So what's the problem? Well, going back to my original model and my original data, the data set that I fit my model on really ranged from something like, -3 to +3 or 4. That was my range of data. I didn't have any data anywhere near 10 with an x value of 10. I had nothing near here. And so this predicted value up here of 105, I end up predicting this value way up here, and that's because I'm just extending my line all the way up here. And that's, maybe that's right, but we really have no idea what's going on in this middle zone. We're really extrapolating beyond the capabilities of our model. And as we get way up here, our accuracy just becomes less and less because we don't have information on that. We don't have anything to validate our model against. We're not sure that we actually can accurately predict out here. So that's what I mean by quantitative extrapolation. And that's when things can go wrong, when you try to extrapolate or look at predicted values outside of the range of the data that the model was originally fit on. The next thing that can go wrong is known as qualitative extrapolation. And so this is where you're trying to predict outcomes for observations that come from a different population. And this happens all the time. This is a real problem in general because often prediction models are built on small samples of a population, and then sometimes they want to be extrapolated or kind of drawn out to a different population that's slightly different or maybe even very different from the one that the model was fit on. And so here, you could still be within the range of the X values. For example, here's a headline from the New York Times from 1988, and this says, "Heart attack risk found to be cut by taking aspirin." And so a prediction model was built to try to predict the risk of heart attack based on whether or not someone took aspirin. And this could include different X variables, like it could include something like age and weight and things like that. And you could be predicting for people kind of within those same ranges and still have a problem. And the main problem here is that this study that was done back in the 80s was just done on men. So the population was men. That is not noted in this headline, but that's the population of interest here. And so if we built this prediction model just using men, but then we try to extrapolate qualitatively to sort of talk about all people, we can end up potentially with a problem. And in fact, here we know that it's the case that women actually react differently to their heart attack risk is not necessarily cut in the same way that men's is by taking aspirin. And so this is qualitative extrapolation, where essentially it's not that you're outside of your X range. You might be exactly within your X range, but you're outside of kind of the range of the population is just different. It's a different population and therefore might not be able to be extrapolated. The next way that things can go wrong is overconfidence due to overfitting. And so, for example, here I've got a relationship between X and Y, and I've tried to fit a model, and essentially I'm playing connect the dots a little bit with this model. So really, especially out here in the tails, I'm basically connecting the dots perfectly with the values that I'm seeing. And so what that means is the error for this model, for example, if I calculated something like the mean squared error, it's likely to be pretty small. I mean, especially by these points, the mean squared error is 0 because my model exactly overlaps with my points. And you can imagine that even in a more dramatic case, I could play exactly connect the dots, where I connect every single one of these dots, and I get an actual mean squared error of 0. And so that model would be very overfit. It would be basically meaningless if you were trying to sort of extrapolate or talk about it in a different population at all, even if you were within the right range, and even if you were within the right population, you're still likely to get the wrong answer if you saw another sample, because we really overfit this model to this very specific small data set. And so this happens when basically we kind of use inappropriate measures to determine whether or not the model is correct. And we're going to be talking a little bit about measures to kind of establish prediction accuracy. But that's what's going on here is if you're establishing prediction accuracy or model accuracy based on the information that this model alone holds, you can basically optimize to play connect the dots with this data. And that's going to be great for this one data set, but it's not going to be great when you get any other data set. So that can lead to overconfidence due to overfitting. So it can look like your model's doing a really, really, really great job, but in fact, it's just wildly overfit to the specific data set you see. And then the final issue is what's known in your book. They talk about black swan events. And in fact, there's a whole book on this concept. But essentially, the problem here is sometimes you can have errors that appear normally distributed because you haven't seen enough data to be aware of extremes. And so this is one of the trickiest ones because here you can do all the correct model checks. You can make sure that you're not extrapolating. You can make sure that you're not overfitting. You can make sure that you are not doing any of these things that we've talked about so far that can go wrong. And yet you can still end up with anomalies because based on the small amount of data that you have, it looks like everything's fine, but there's maybe some rare extremes out there that can really skew your data. And so one area where we see this often is in financial applications, for example, things like stock prices. Those are often characterized mostly by small changes. So usually if you were trying to model this, your errors would be normally distributed. But there's infrequent, very large changes, like these huge downturns that can happen. And those will really kind of throw a wrench into your predictions because all of a sudden it can look like you're doing a really good job predicting, and then all of a sudden you've got this value that comes out of nowhere that really wildly, you end up really not getting the right predicted value for that. And so these kind of black swan events, this is one that can be kind of hard to guard against, but just sort of keeping in mind, particularly kind of depending on what application you end up going into.